Hello, my name is Michail Stamatakis and I am Professor of Computational and Organic Chemistry at the University of Oxford. In my group, we develop and use multi-scale computational methods to model, simulate and predict the properties of catalytic materials for different applications, such as emissions control, biomass conversion or carbon dioxide conversion. Such applications are key in the development of efficient technologies and the improvement of the quality of life.
Hi, my name is Hector Prats and I'm a postdoctoral research associate at the Stamatakis lab at University of Oxford. I'm working on the computational design of active, selective and stable catalysts for the conversion of methane and carbon dioxide, two well-known greenhouse gases. And one of the motivations for this research is their abundance. For instance, large amounts of methane are available in nature in the form of natural gas, while substantial amounts of carbon dioxide are generated by human activity. So if we can use these two gases to produce more valuable chemicals or clean fuels, this will be very beneficial for the overcoming ever-increasing energy demands and to achieve a more sustainable future. But this requires the design of active and selective catalysts. Among promising catalytic materials, transition metal carbides have gained popularity in the last decades because they are highly refractory and resist sintering, coking, and sulfur poisoning. In a nutshell, transition metal carbides are obtained by incorporating carbon atoms into the lattice of transition metals of groups 3 to 10, although only those of groups 4 to 6 have been extensively studied, both by theory and experiment, because they are thermodynamically more active. In general, metal carbides possess unique physical and chemical properties due to a bonding that involve covalent, ionic, and metallic contributions. This results in transition metal carbides displaying properties characteristic of three different classes of materials. For instance, they have the extreme hardness and brittleness of covalent solids, the ordered bulk structure and high melting points of ionic solids, and they also exhibit the excellent electrical and thermal conductivities characteristic of metals. And ever since the landmark paper by Levy and Boudard in 1973 regarding the platinum-like properties of tungsten carbide, metal carbides have been the subject of many experimental studies, often accompanied by theoretical investigations, showing that their catalytic properties are similar to those of noble metals for a variety of reactions, such as desulfurization, methane reforming, or the water-gas reaction. But they are much cheaper than noble metals. Apart from the use of transition metal carbides as catalytic materials, a new line of research originated in the late 2000s on the use of carbides as supports for small metal particles, demonstrating higher activities and selectivities than when these particles are supported on oxides. For instance, small nickel clusters supported on titanium carbide can activate methane at room temperature, which is quite challenging because methane is a very stable molecule. And this enhanced activity is attributed to a strong polarization of the electron density of the metal particle when it's supported into a carbide, which makes these supported particles very reactive and can facilitate the bonding of certain molecules. Moreover, unlike traditional oxide support materials that are inert, carbides are active supports that can also catalyze different steps of the reaction. So the combination of a carbide with a metal particle leads to a bifunctional catalyst with multiple active sites, allowing for cooperative effects. And since then, a significant number of works have reported outstanding catalytic performance of carbide-supported metal particles for a variety of reactions, such as the water-gas reaction or CO2 hydrogenation. To date, however, only a very small subset of carbide-supported catalysts have been tested experimentally. In our group, we have used supercomputers to predict the stability and catalytic performance of many different combinations of metal clusters supported on carbides towards methane and carbon dioxide conversion technologies, and we have identified several combinations that are very promising. In this perspective article, we summarize experimental and theoretical works on the use of carbides as supports for metal particles, and we identify the key factors defining activity, selectivity, and stability. We also illustrate important trends for the rational design of novel carbide-supported catalysts with the aim to shed light on future development on these materials.